Electrons occupying the energy shells in an atom take the form of a cloud surrounding the much smaller nucleus. Since only 2 electrons can fit into each of the energy shells, it is interesting to look at the characteristics of these different shells or energy states. These states are defined first by a primary quantum number called n, and also by a secondary quantum number called L. And for each state, the electron has a different energy, which results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the same in all directions. For n equals 2, the shape can take 2 forms depending on the value of L. Although both shapes have the same energy, one shape is a double spherical cloud, one sphere inside the other, while the other shape for n equals 2 is in the shape of a dumbbell. For other values of n and L, the shapes can be pretty strange, like this torus plus dumbbell shape. An electron in the lowest energy shell in an atom can be struck by and absorb the energy of a photon, giving it enough energy to jump to the next energy shell. And the reverse process allows the electron to jump back down into the lowest energy shell and emit a photon. The color of the photon depends on the energy difference between the 2 shells. This explains the spectral lines that identify an element. Since white light contains all the colors in the spectrum, when we shine white light on a sample of an element under the right conditions, the atoms absorb all the photons that allow their electrons to jump to other energy shells. So, the absorption spectrum is all the colors in white light minus those that match the difference in energy shells within the atom. And when those electrons spontaneously jump back down to the lowest energy levels, that emission spectrum contains only the lines that match the difference in the energy shells within the atom. Here is a piece of spectra from hydrogen. The primary quantum number n is shown on the right alongside the line representing that energy level. When an electron jumps from the n equals 3 shell to the n equals 2 shell, red light is emitted. When an electron jumps from the n equals 4 shell to the n equals 2 shell, aqua light is emitted. When an electron jumps from the n equals 5 shell to the n equals 2 shell, blue light is emitted. When an electron jumps from the n equals 6 shell to the n equals 2 shell, violet light is emitted. When an electron jumps from the n equals 7 shell to the n equals 2 shell, ultraviolet light is emitted. No jumps to n equals 1 are shown because they are all in the deep ultraviolet. We begin our climb up the ladder of structure by noting that there are 2 kinds of quarks that are found in normal matter. Physicists call them flavors of quarks. These quarks are the up quark and the down quark. A proton is formed from 2 up quarks and 1 down quark, while its slightly heavier cousin, the neutron, is formed from 2 down quarks and 1 up quark. The red, green, and blue colors of the quarks represent a property that attracts them to one another. It is this color charge property of the quarks that hold them together in a proton or a neutron. These protons and neutrons can then combine to form the nucleus of each element in the periodic table. One proton in the nucleus makes hydrogen. 2 form helium. 6 carbon. 8 oxygen. 79 is gold. And 92 uranium. Neutrons help hold the protons together. Because of their electric charge, protons would repel each other more strongly if neutrons were not present, and the heavier elements would come apart. There are approximately as many neutrons in each element as there are protons. Atoms are formed when the positively charged protons in the nucleus capture the negative electrons. Neutral atoms capture one negative electron for each positive proton in the nucleus. So, hydrogen has one electron to go with its one proton. Helium, 2 electrons. Carbon has 6. Oxygen, 8. Gold has 79. And uranium, 92. There are nearly 90 stable elements. The largest of them contain close to 800 fundamental particles joined in a complex but stable structure. But electrons cannot just gather around in a crowd. The strange, wonderful world of the tiny has some quantum idiosyncrasies. Electrons arrange themselves in shells inside an atom like the layers of an onion. And only 2 electrons can fit per layer. So the more electrons an atom has, the further away from the nucleus the outer shells must be. And that means these electrons are more loosely held. It is this difference in how tightly electrons are held in each different kind of atom that determines the chemical properties of the element. This accounts for the ability of metals to conduct electricity, the aloofness of noble gases, and the formation of molecules. It turns out that protons in 2 or more different nuclei can sometimes capture and fight over the same electron. And when that happens, atoms of different elements are joined together to form molecules. This oxygen atom is sharing 2 of its electrons with 2 hydrogen atoms. This is how a water molecule is formed. The periodic table is a list of all the atoms in the universe that have different numbers of electrons. Hydrogen has 1 electron. Helium has 2. Carbon has 6. Oxygen, 8. Gold has 79. And uranium has 92. Today we know that it is the arrangement of electrons inside each atom that determine the chemical properties. And similar arrangements lead to similar properties. And although each electron in the atom needs 4 quantum numbers to uniquely describe it, we only need to talk about 2 of them in our discussion of the periodic table. The quantum number n determines the gross energy of the electron in each orbital, with some adjustments for the other numbers.
and the quantum number L determines the shape of the orbital. All of the elements in the table are arranged into groups based on different values of L. Elements in a given column have their outer electrons in a similarly shaped orbitals, and this means they have similar chemical properties. This is the S group. It has L equals 0, and each row in this group can hold 2 electrons. This is the P group. It has L equals 1, and each row in this group can hold 6 electrons. The L equals 2 group, called the D group, can hold 10 electrons per row. And the L equals 3 group, called the F group, can hold 14 electrons per row. In order to fit the table into a narrower space, the F group is often listed below the rest of the table. But we will put it into its rightful place and just deal with a wide but correct periodic table. Notice I have included helium in the S group next to hydrogen. But I have also duplicated both elements at the right end of the table with the P group. Their chemical properties make both of these alignments useful. In a given group, N increases by 1 for each row in the table. So the outer electrons in the elements, directly below other elements, have more energy and are less tightly bound to the atom. As we add electrons, one after another to atoms, each new electron occupies the lowest available energy state. And so it is the energy levels of the electrons' orbitals that determine where the different L groups fit into the table. The periodic table lists all the substances in the universe that have only one type of atom in their makeup. Countless millions of other substances are made from combinations of these atoms. When atoms come together, they form bonds, and the resulting molecule or compound has a whole new set of chemical and physical properties. So let's look at chemical bonding and start with the most abundant atom in the universe, hydrogen. The element hydrogen has 1 proton and 1 electron, making it quite simple. The proton is positively charged in the center of the atom, and the electron is negatively charged and occupies a larger space outside the nucleus in the form of an electron cloud. This electron cloud surrounding hydrogen is often called an orbital. It is basically all the places where an electron has a chance to be found. Now let's bring another hydrogen atom into the picture. As we slowly start moving them closer to one another, we will show their combined energy on this graph. For a while, nothing changes. And then as they get close enough together, their energy starts to drop and eventually hits a minimum. And this makes the combination stable. This minimum energy distance between them is called a bond distance. And they are now sharing electrons. This is called a covalent bond. And instead of having 2 individual hydrogen atoms, we now have an H2 molecule. Moving the atoms any closer increases the energy greatly, since the positive protons in each of the atoms are repelling one another strongly. Covalent bonds come in different lengths and strengths depending on the atoms involved. These bonds are often shown as posts, lines, or dots between atoms. But of course, these are simply representations of places where electrons spend their time between atoms. In a covalent bond, electrons are shared, but they aren't necessarily shared equally. Let's take one of the hydrogen atoms and replace it with a fluorine atom. Watch what happens to the electrons throughout the atom. Fluorine, by its very nature, has a stronger pull on electrons in this molecule than does hydrogen. Fluorine shares electrons, but not equally. Instead, it pulls electrons closer to itself than to hydrogen. This is called a polar covalent bond. Each element in the periodic table has a tendency to pull electrons towards itself in a bond. This property is called electronegativity. When you alter the periodic table to show electronegativity, it looks a little different. Notice that elements on the left-hand side of the table, metals, have very low electronegativity values. They don't pull electrons towards themselves at all. As a matter of fact, they willingly give them up entirely. Table salt, as we know, is made up of sodium and chlorine, and so it is called sodium chloride. In forming table salt, the sodium atom gives up an electron and becomes positively charged. The chlorine atom picks up the electron since it is more electronegative and becomes more negatively charged. Now a very old saying takes over. Opposites attract. So here, the atoms are drawn towards one another by their positive and negative charges. If there are enough atoms, we can eventually wind up with something as big as a single salt grain. This kind of bond is called an ionic bond. It is a very strong attraction between positive and negative ions. Most people differentiate this from a covalent bond by saying that in ionic bonds, electrons are exchanged instead of shared. Ionic bonds are very strong, stronger than covalent bonds. And you can easily see this difference. Melting sugar, which is breaking a covalent bond, is simple and makes caramel. Melting table salt is very different and requires temperatures higher than 1400 degrees Fahrenheit. Ionic bonds are very stable bonds. Very important, and much weaker than ionic or covalent, is a hydrogen bond. When hydrogen atoms connect to a small, strongly electronegative atom like fluorine, oxygen, or nitrogen, the resulting molecule pulls the electrons so strongly to the larger atom that the hydrogen nucleus, its one proton, is essentially exposed on one side. So it will bond to the negative side of any similar polar molecules. This bond is called hydrogen bond. The difference in strength of the different types of bonds is fundamental to allowing the DNA molecule to replicate itself. The bonds that hold the opposite sides of the double helix together, the A's and the C's and the G's and the T's, are hydrogen bonds and are very weak compared to the bonds that hold each letter to the backbone and the bonds that hold the backbone together. This allows the molecule to unzip easily, to expose one side as a template for replication. Life is all about bonds. Bonds, chemical bonds. Who knew?